All right. Thank you very much. I'm just going to get started right away because I know that I'm going to want to go over on time on this one. So this talk is a talk that I think is kind of crucial to what we're doing because we've worked. So what has the SciMo organization been doing? Right, we've started a lot with numerical methods, and we kind of started doing a lot with the scientific machine learning, and then this whole symbolic thing came up, and I think a lot of people have been kind of like, "Don't you work on numerical methods?" And I think I've always been saying like, "Oh." We want to do symbolic things because they'll build us a better numerical solver than we could ever do by hand, right? And I want this talk to really show you exactly what we're doing. I would say, still in progress. The things can still be used. We haven't turned everything on by default, but I want to show you what exactly is going on in the ecosystem, so you can know, where are we getting the next 10x, where are we getting the next 100x of performance, right? So let me start with a quick introduction to SciMo and our numerical methods, right? SciMo is an organization that has these differentiable numerical solvers that are highly optimized for all sorts of different systems, right? This is actually just one subset of them, right? The linear solvers, nonlinear solvers, differential equations, which has ODEs, SDEs, optimization tooling, integrals, and things for partial differential equations, right? So this is what you kind of know and love of the numerical part of SciML, and this is the part that we've really kind of developed over the last 10 years. This is kind of our core, right? When people think about SciML, the first thing that they usually will go with is they'll say, "Oh, differential equations.jl," right? This is the thing that was 50x faster than scipy, 50x faster than MATLAB. It has all those benchmarks. But the key that really made it so that way, is not just another ecosystem, was when we started being able to show that, here's this performance improvement over the C and Fortran methods, right? When I actually started a lot of this, I was told, oh, nothing will ever beat, LSODA. Nothing will ever, ODEs have been done. It finished in the 90s. And what we found was, there's a new numerical methods that could do this, right? There are numerical methods that are already in the literature. There's new things that the way that computers are being built changes the way that you have to build algorithms. And we really kind of brought this forward with all these new solvers. But, as you continue to do that, we're still continuing to make numerical methods, but that tends to saturate, right? You start to be able to say, oh, I'm 2 times faster, 3 times faster. No longer you get the 100x all the time if you're trying to start battling against yourself, right? And so, what I want to do then is I want to kind of introduce, like, what can we start to do in a very hands-on kind of way, right? So let's take a problem that is kind of simple, right? So here's a linear system. We want to find the U1, U2, U3, U4, U5, such that this system is satisfied. U1 equals U of 5, U2 equals cosine U of 1, right? It's some nonlinear system. And I think most people here, like, you got your laptop out and you're like, all right, I know how to solve that system. You write it down and you put it into a Newton method, right? That's what you do. So it's a system of five variables, and you want to solve for 5 different variables in a system of 5 equations. We throw it into a Newton method, right? And okay, so that's what we did. We as an organization that works on a lot of numerical solvers, we actually just got a publication. I think I got the email that was accepted a few days ago, but I didn't read the full email. So, I think Avik said, though, it's now accepted, that, we have this publication now that shows, oh, nonlinearsolve.jl is by far the fastest, nonlinear solver. It's outperforming MinPack. It's outperforming Sundial. So, we've done this not just for ODEs, but also for nonlinear solving, with these tricks of trust region and other ways of doing, Newton methods. So you just call a Newton method, you just make it good. One of the things I want to highlight here is that, again, these algorithms have been really optimized over the time. So when we say we're doing better, we're saying, like, oh, when it's head to head, we maybe have like a 1.5x speed up, a 2x speed up. It matters a lot because a lot of people are doing Newton methods, but it's not going to be that huge changing. Well, where the huge changes come from end up being these compiler integrations, though, where we say, okay, you give me a code, I will find your sparsity pattern for you, and I'll determine whether I should use a sparse solver or not. And, oh, if you didn't know that you should use a sparse solver, we will turn it on, and boom, now you got a major performance gain, right? So we get a lot of gains through these kind of looking at your code and automating things, but the numerics is still kind of saturating, because how much can you do with the Newton method, right? So, but we do, yeah, go ask a question.
We got like on these heap dominant or these paths are common. So you read at these T upside to board across, so like,
Yeah. So the question, I think your microphone is muted, but the question was, does this hold across a bunch of different problems? Yeah. So what we had to do for this paper is there's actually a whole test benchmark, which is 23 different nonlinear problems that is from a test set that we pulled in. There's also a lot of other problems pulled from industry, right? So the one I'm showing here is a DFN battery model and its initialization, right? And we've also collected a lot of problems from the organization, from people in the community. So if you go to the SIMO benchmarks, you can see that there's, it's benchmarking a set of 35, 40 problems. And our methods do not do the best in all cases, right? But on average, over, I think that in 37 of the 40 problems, we are now doing the best, right? And for the other 3 problems, that becomes its own research project. Okay, what do we do there, et cetera, and continues on. But yeah, if you think that you're on your problem we don't do good, please just submit that as a pull request to our benchmarks, and so that way we can see how bad are we doing on that benchmark. We want to see that because then we'll spend the next few years making it better, right? And that's effectively why we do well in the benchmarks, right? We look at this every day and we just say, you wake up in the morning and say, how could I do better on this benchmark? And then you go say hello to your dog or whatnot, right? But it's always, how do we do better on this benchmark, right? And so at this point, again, you could wake up, you just say, this is a Newton method. I put this into nonlinear problem, and if you've seen the nonlinear solve talk or the documentation, you just write it down where you just say the residual equals, move everything to one side, you call nonlinear solve, and boom, you solve it. Done. This is what everyone does, right? C does this, Fortran does this. We have some good numerical methods, but everyone does this. So what else could we do? Well, what if we were human, right? If I was a human and I was like to look at this problem, I would not solve it by trying to find all 5 variables at the same time, right? What would I do? Well, what I would do is I would say, well, look at the first equation, u1 equals u5. Let me just substitute that into the other equation, right? So u2 equals cosine of u1, so therefore u2 is equal to cosine of sine of u5. And if I just start substituting things together, what I'll find is that there's an equation at the end, which is u5 equals gigantic mess of only u5. This is a scalar equation. But if I solve this scalar equation, I can substitute everything else together, and ta-da, I'm done, right? So if I was a human, I wouldn't solve 5 equations at the same time. I would just solve this one, and I would do everything from that. And so what we started to do is say, okay, how can we put what the human smart person would do and put that as part of the numerical algorithm? This is symbolic numerics, right? Where you say, okay, give us the structure of your equations, and we're going to actually modify the equations, and we're going to compile something after we've changed your equations, and we're going to do the numerics on a changed form of that equation, right? So symbolics and ModelingToolkit come before the numerical solver. It comes before the differential equation solver, the nonlinear solver, or any of these pieces. So you've taken the whole ecosystem and made it so that way there's a symbolic part that could go in front of it. And so what we can do now is we can say, hey, here's a symbolic representation of the nonlinear system. Now simplify it for me, right? The simplified version of this equation system is one equation, and there's 4 other equations you can derive from that. And now when you solve the equation, it only gives you out one value, right? Because even though you gave it 5 equations, it solved one equation, but it just knows how to generate all the other solutions from that, right? So now we can be kind of smart, right? And the question is, how much did our brains actually help? If we actually look at what's going on inside the Newton solver, right? The Newton solver uses an LU factorization, which is O of n cubed, right? So as you make these systems harder and harder, the cost numerically grows like cube, right? So if we make that system smaller, then we don't just like, if you half the size of the system, you don't half the computational cost. You take the computational cost by 1/8 down, right? It's an order of magnitude just by decreasing the system by half. So this really means that, okay, even if we can just start to simplify out even small parts of it or something, we can still get major performance gains just by saying, oh, this is an easy part. This is an easy part. Right? But then we can also start to do other things, right? We can say, hey, look, here's a big system of equations. And, if I was a computer, I would say, let's run a Newton solve on the big system of equations, right? But if I was a human and I looked at this problem, I would say, the first 2 equations only use u1 and u2. So let me solve that first. And if I, in the next 3 equations, only use, u3, u5. So let me solve that first. And then the last one uses all the equations, so I'll solve that using the results of the first ones. But not only that, but the last one is linear, so don't call the Newton method, just use a linear solver instead, right? Like if I was a human, I would look at this and I would do this on the whiteboard, and I would say, oh, the reason why numerical methods don't work well in my domain, quantum physics, is because people have realized that we have to specialize the equations like this. No, the problem is the numerical methods should be specializing your equations, and if you're just putting it into a numerical solver, it won't. So what can we do here? Well, what we can do is we can make it so that way we have a set of this new SEC nonlinear solve, which says, here's a way to be able to do this cascade of nonlinear solvers, where you can say, solve the first problem, solve the second problem, solve the third problem using the results from the first and second, and actually make that one linear and tie it all together, right? So now we can do these cascades of problems where you say, hey, look, this is actually the more optimal way of solving it, split it apart. And then what we can also do is we can make it so that way the ModelingToolkit front end, the symbolic front end, does this analysis, figures out how to cut everything up, and splits it for you, right? And so this is what we've been able to do. So this is now this has been a standard part of ModelingToolkit for a while, right? And we're continuing to prove. So as as Aisha had mentioned, right? We're continuing to improve this, where you can start to say, hey, look, symbolics.jl now has a symbolic ODE solver, right? Or a symbolic nonlinear solver. So if you give it polynomial equations, it can try to find if there's a symbolic equation. And so now we can start to say, hey, look, let's cut this into little portions, right? As you solve this one, then you solve this one, you solve this one. Does this piece have an analytical solution? If it doesn't have an analytical solution, what do I know about it? Can I transform it into a polynomial system? It basically tries every little trick that is in the literature. I think everyone always says, you have to use your, I have to write my own code for the way that I do, my chemistry domain, because I know how to make these things solve better, right? Well, every single trick that you do, we can stick it into the symbolic system and automatically put that in front of the numerical solver, so that way it tries it, right? And so we're just growing and growing and growing with these terms. And so this is why we're talking about symbolic numerics, right? These are things where people say, you can't just use the numerical solver. And I think we agree that you can't use the numerical solver, but we don't agree that it can't be automated as part of the numerical solving process, right? And so all of these little tricks, all these different analytical solutions, we're then piecing it together as part of this pipeline for the solver. And then the next piece here is to say, okay, this has just been about how you solve a nonlinear system. Let's go back to ordinary differential equations. Can we use this so that way we can build an ODE solver that is doing so well that people will effectively accuse us of cheating in benchmarks, right? That's my goal. I want people to ask this question, like, are you cheating in your benchmarks? Because if we are doing so well in our compiler that it is, finding your sparsity pattern and doing all these things that people are like, but scipy isn't allowed to do all that, so is that really apples to? I want it to be a non-apples to oranges comparison, because that's how you're going to get the best solver, right?
Can I just make a funny observation here? This point about cheating in benchmarks, I think one of my grad student from my days, one of my advisors, I was literally told that Chris Rackauckas and his gang are terrorizing people at conferences with their data.
Yeah.
Well, this is a real complaint that I have received.
Yeah. So So if our solver is faster on this equation because we replace the numerical solution with an analytical solution, people do accuse us, you're cheating that benchmark, and I say no, make your algorithm go faster, right? This is a valid thing. The analytical solution is true, so we're using it, right? And I think that so that was without ODEs involved, right? Now how do we bring all of this to the ODE domain so that way we can continue to cheat even better, right? So in order to figure out how to do this, let's take a quick primer on implicit solvers, right? So an implicit solver, if you want to solve a differential equation, the simplest one is the implicit Euler method, right? UN plus 1 equals UN plus h f of UN pt, right? And you say that, if you go to a stiff system, you have to use this kind of solver, and because it's good for, systems that are stiff, that have large eigenvalues, yada, yada. But, but UN plus 1 shows up on both sides. So what do we actually do inside of this equation, right? Well, what we do is we move everything to one side, and we say, hey, if we know the previous step, UN, we know our step size, we know the parameters, and we know Tn, then all that we're solving for is UN plus 1. So we need to solve an equation, G of UN plus 1 equals 0. I just told you that's a Newton method, right? So what every single nonlinear solver, what every single ODE solver does today is they say, let's take your system of ODEs on that exact function, and let's solve a Newton problem for that whole equation. But should you actually do that? I just told you all the different tricks that we could do if you had a nonlinear system. Here's a nonlinear system. This is the slowest part of our stiff ODE solver. Can we just change that as well? Right? So here, let's take an ODE. So here's the Robertson equation. We show this many, many different times. It's a chemical reaction system, right? So, and anytime you're going to solve this, you're solving for 3 ODEs, and so every single time you have to solve a Newton method for 3x3 systems. So you have O of 3 cubed as your cost, yada yada, right? But let's do this little bit. What I'm doing in here is I'm basically saying, hey, symbolically go through and generate the exact same equation that is being used inside of the nonlinear solver for the FBDF method, and now run structural simplification on it. And what it does, if you look at this equations line, I don't know why my pointer's not showing up. You look at the equations line, it says the equations for the nonlinear solve in the middle of the step there is I can actually solve it by just solving for one variable, and I get all the other ones for free. Because it did, again, I just told you all the tricks that it's able to do. But if I take this simplified version of the nonlinear solver and I stick it within my FBDF method, right? If I inline in this nonlinear solver and outline the ODE solver, I can then use this simplified version of the numerics. And now it's specializing it specifically only to your solver, but it's now turned it into a problem that is, from 3x3 systems to 1x1 systems. And again, the cost of this is cubed with the size of the system. But not only that, we can actually do this in a form where we can say, if you use this form, mx plus outer TMP, and we rewrite the ODE solvers, then what we can do is we can make it so that when ModelingToolkit can generate exactly one form of a nonlinear system and make it so that way every single ODE solver is able to use that exact nonlinear system. So we can compile one piece of code that is, hey, here's the optimized form of solving this weird piece right here. And then every single stiff ODE solver goes, hey, in my internals, I can reinterpret what I'm doing to be that piece. And do you have an analytical solution for me? Do you have a optimized piece for me? And then we can use that symbolic-numeric generated piece in the middle there. And so effectively, what we're then able to do is, for this system of 3 equations, we're actually only solving one set of equations at every single step and knowing how to interpret it back up to 3. So now, again, yeah, we're cheating because we're only solving one equation and we're getting all 3. And this is what we now have as the NL step interface. So in ModelingToolkit, this is not done by default yet because, again, there's still a lot of moving parts to this ecosystem. But if you tell it NL step equals true, what it'll do is it'll generate this nonlinear system. It will simplify it down. And then you can tell it to use certain ODE or nonlinear solvers. Again, the nonlinear solvers that you use here are the nonlinear solve.jl ones, right? Everything in the ecosystem is piecing together. And now you can say, hey, solve this with FBDF. And so the first order, second order, third order, fourth order, fifth order BDF, it doesn't matter which, as it's adapting its algorithm, it's always going to use this optimized version of the nonlinear solver because of the way it's being retargeted. But not only for FBDF, you move it to an SDIRK method, it's also going to use this. You move this to Rackauckas method, well, the Rackauckas methods will need a little bit more, but you could also use this, right? And so basically what we've done then is that we made it so that way the symbolic ecosystem is able to reach into the middle of the ODE solver, find its most expensive piece, be able to reconfigure it and simplify it down for your specific problem, and then inject a function right into there so that way during its solving steps it can use that optimized piece. Again, there's still a lot more to do here. So this all works, right? This is all working code. This is, the tests are all on and everything. I think that what we still need to do is we still need to do some performance improvements because there's still some allocations going on in the way that we're shuttling things between different solves. And so we need to make sure that we fully do out the caches and we fully do out the way that we do the reuse steps. But what we see already is we're already seeing, even though it's allocating, it's already faster for a lot of cases. And so once we get all the performance improvements in, we should be doing quite well. One of the other things that we haven't done as well is as I mentioned, we can cut things up so that way, instead of solving one big problem, we cut it up into 3 problems. It turns out that we cannot do this chopping up in the middle of the ODE solver right now. That's just because of some things within the interfaces. Specifically, SCC nonlinear solve needs to have a caching interface where you can define a nonlinear solve once and then change the parameters and just reuse the same caches over and over. That interface does not exist. So like the integrator interface on nonlinear solve, that does not exist on the SCC portion right now. We need to fill that out and then but these little details in the middle just to really make it so that way all of the tricks and all the SCC portions can be all applied within the ODE solver, and then we'll be coming out with our the major benchmarks. But the thing there is, yes, it will look like we will have cheated in those benchmarks, and I think that it depends on your definition of cheating. I believe that if your compiler can do all this automatically and can replace your entire numerical solve with a bunch of analytical solutions, I am happy to say that that's how we do it, and get on my level. So, continuing the R&D, I think that there's a lot more that's going on in this space. Alexander Demmin, I think, is one person I'd like to highlight who's been doing a lot of very interesting work in being able to not just on nonlinear systems, but also find out how to be able to rewrite ODE systems as equivalent forms. So that way, instead of solving, here's a case that's really easy to identify, where instead of solving 4 ODEs, you can solve these 2 ODEs. If you mix this with the way that we do the nonlinear solving, you can end up with solving a scalar equation for the set of 4 polynomial or differential equations. And so, you start to mix all these different tools, you start to have, ways to use analytical solutions on this part, this part, this part, this part, and they could all be quite different. And again, I just want to highlight another thing that ModelingToolkit does that they should be aware of. There's a lot that we're doing for performance, but a lot of this actually doesn't just matter for performance, but also for numerical stability reasons, right? If we replace things with analytical solutions, we no longer numerically require that, hey, if the Newton method converges, then x squared plus y squared equals 1. When we do these analytical solutions, x squared plus y squared equals 1 is built into the analytical solution of the system, and it cannot be broken. Right, so you start to get a lot of these features, like like conservation of energy is just a result of the system, because we do not have the numerical solve that causes the drift and the numerical error in these kinds of properties, right? And this is also mixed with a lot of things in ModelingToolkit, where you can say give it a differential algebraic equation, and it can then change it to a different differential algebraic equation, which is numerically easier to solve. This is the DAE index reduction pass, right? So again, we're mixing things that are specifically for improving the stability of the numerics with things for analytical solving, with things for simplifying down the systems that are being solved, and then also cascading them into multiple systems. And I think that this is the way forward, right? I think that this, the promise of Julia was that we don't have something where the compiler lives separate and you write numerical methods on the compiler. This is something where we started to say, hey, it invites numerical people to start working with the compiler, right? Multiple dispatch means, hey, use multiple dispatch to write your own compiler and integrate with the system. And if you're to give a numerical analyst a compiler, this is the cookie they come up with, right? And I think that this is still something where a lot of new projects are going on. In fact, everyone who's thinking about, I want to work with MIT in the Julia lab, all of them, I'm telling them, we do a lot of scientific machine learning, but the scientific machine learning integration with symbolics, this is what this is really the future. And so if you want to talk to us about projects, we have a project list, and we'd be happy to start getting you in these collaborations, because I think that these kinds of techniques are everything that is going to be down the line, all the major pieces. So thank you very much.
So I have multiple, let's say, devil advocates questions, right?
Yeah.
One is there are situations where actually extending the problem simplifies the numerical solution, right? So homotopy methods and stuff like that. And like biasing the search to say we'll always try to reduce things symbolically is you're trading off continuous optimization with discrete optimization, right? Symbolic search is essentially discrete optimization. So are you sure, and have you seen this in your benchmarks, that going via symbolics always, like in total computation time, always reduces the complexity?
It doesn't always. It doesn't always. Yeah. But also, there's, again, you make this statement that says, oh, there are some cases where you have to use homotopy methods, right? ModelingToolkit can target homotopy solvers, right? This is one of the things that Ayush had talked about, right? And B, my question to you would be, what kinds of systems would you do this on, right? What would you look for inside of a system where you'd say, hey, let's target a homotopy method instead of the other method?
I'm asking the questions here.
Well, yeah, but if you give me that, then we have a way to target the homotopy methods, and we will just do that, right? Like, this isn't something you say, like maybe you should try this. The algorithm can be look for that property, and if you have that property, generate for a homotopy continuation problem instead of nonlinear problem, right? And so I think that if you think about it in the wider, yes, there's certain algorithms that we're doing here, but if you think it in the wider symbolic numeric mindset, right? I think that your problem's not actually a problem. It's more of like, what's the algorithm, right? Well, you got to do it to the microphone, so that way the beautiful, beautiful viewers online and in the video and the ones who live on YouTube could hear as well.
Sounds good. Just following up on that question though, because as you're kind of in some problems, you're switching computational complexity from the solver to the simplification or structural simplify.
Yeah.
And is the solution for that, and I'm having the back of my head like polynomial systems, and sure, once you find like a Grosvenor basis, you're done, right? But you've switched all the computational complexity to that. But so is your solution for that just finding some way to identify like the dispatch in the structural simplify that you bake in to that?
Yeah. Being able to identify, is this useful? Should we do it or not? Yeah, that could be based off of heuristics and benchmarks, but also just generally making that part faster, right? The first talk in the symposium was the hash consing talk. The second one was the modeling toolkit talk, and they all talked about how we're identifying shared structure and making systems simpler and improving the simplification passes, right? It really goes hand in hand, right? That we really need to make the symbolic simplification needs to get better. In fact, the compilation of the functions that we generate from these analytical solutions, that needs to get better. And we need to piece all those together in order to get a system for which this all makes sense. See, that's why I mean that there's a lot of moving parts, right? There's these parts of like, if we start to do all these integrations and we're generating this function and we're inlining into the solver, is the solver compatible with Julius C? And can you precompile to a binary still, right? Like, how do all of these things need to be answered in order for it to actually be a good snappy system, right? So yeah, there's in some sense, sometimes you're trading numerical performance with compile time, right? Does this make sense for your given problem? I think that what we plan to be doing is we plan to just be giving all of the knobs, right? With heuristics on top, right? That's what we generally do with the differential equations and everything, right? We say, here's 400 solvers, but here's a default, right? We're planning to do this with the whole symbolic numeric system where we say, here's a structural simplified, but you can also tell it, NL step true or false, or allow analytical solutions true or false, and it'll basically look at it and go, yeah, if you have a partial differential equation with 2,000 equations, I'm not going to go through and try to analytically solve every equation in here, right? But maybe you'll try to analytically solve small sets of equations and such. So it's a game of ever improving heuristics and ever improving. I think the key here is to really kind of structure this then as something where you say, okay, we have these different parts of the system, the numerical methods, and we're really exposing, hey, there's a system in the middle here for doing transformations. And what we want to allow you to do is we want you to be able to, we want to put every single pass possible in here, and then we want to put heuristics on it, but then allow you to control this piece. And then, improve modeling toolkit, improve symbolics, improve the meta theory, the symbolic we just need to continue to improve all these layers, and whichever ones tend to be working in the end, these are the direction that the heuristics push people towards, right? So and this is why I kind of say this is kind of open-ended talk, because there's one direction that seems to be working really well right now, but again, there's a lot of other things, for example, using E-graph simplifiers, which we had I think Alessandro had a nice paper on a few years ago. Bringing back some of these E-graph simplifiers is also one other technique I haven't even touched on here that can also improve a lot of these systems, right? So there's a lot of these different techniques at play. There is a trade-off always when you do these, that you might be doing more analysis up front. So yeah, if you want the lowest latency version, probably doing the classical numerical approach of just throwing in the solver is the best. But if you're going to be, say, putting this into an optimization loop, for example, one thing that we haven't quite done yet, which we're definitely going to do though, is, hey, if you want to do reverse mode automatic differentiation on your piece, right? If you do a stiff ODE and solve going forwards, you also have a stiff ODE solve going in reverse for the adjoint method. Can we take the ODE that's generated by the adjoint method, take its nonlinear solve and simplify that down too? I mean, if you're waiting 4 days for your optimization to solve, maybe you're willing to wait 5 hours to be able to get a really nice one, and generate a binary from that, so that way we keep that function around. around, and boom, just slam through all these optimizations, right? So, it's always a use case thing. And there's a lot, and I think that we need to do is we need to just get out as good as possible and then enable these different use cases to be able to say, hey, I care about, latency. I care about making it as fast as possible. I care about numerical performances. And these will all require different kind of paths through the system.
Sounds good. Yeah.
Right. Do we have any other questions for the speaker? If not, let's thank Chris for the fantastic talk.